Hello everyone. My name is Dr. Ranjith Kumar Gatla. I'm working as an associate professor in Department of Electrical and Electronic Engineering at IARE. So today we are going to discuss another topic from the module 1 of the course Power Electronics, which is series and parallel connection of the SCR. So in this course we are going to discuss what is the need of connecting the different SCRs in series and different SCRs in parallel. Okay, so these things we are going to discuss in today's class. So here, as we can see, nowadays the SCRs, of course, the high rating SCRs are available in the market. So which is about up to, when coming to the voltage, which is up to 10 kV, and when coming to the current, which is up to 3 kiloamperes, thyristors are available in the market. But sometimes we face demand more than these ratings, which means in some other application, okay, so we may need the thyristor, the rating, so which may more than this 10 kV, and in terms of current, even it required more than 3 kiloampere capable thyristors. So in those cases, okay, so we are going for the series and parallel connection of the SCRs, which means, as we know, suppose if any application need high rating, voltage, that capable thyristor, so in that case we connect the several SCRs in series. Similarly, the parallel connection of the SCRs meets high current demand. So based on the current and the voltage rating of an particular application where we need the thyristors, so in that case, based on the voltage and the current ratings, so we will connect either in series or parallel, so based on the voltage and current rating requirements. Then, but of course, then while connecting the SCRs, the different SCRs in series to get high rating capability, then what are the conditions that we must take care, and what are the conditions that we must satisfy to get connect the more than 2 SCRs in series, right? So although the SCRs in a string, okay, are having the same rating, but the VI characteristics of an SCRs are different from one other, because the voltage sharing between the two SCRs may or may not be equal. So the voltage sharing between the two SCRs is different. So that's why the VI characteristics of the two SCRs are also different, even though the two SCRs having the same rating. So that the SCRs not fully utilized. So here I have just mentioned the string efficiency. So the string efficiency is based on how the the SCRs are utilizing, whether the SCRs are fully utilizing or not. If the SCRs are fully utilizing, then the string efficiency will be 100, or if the SCRs is not utilizing, if they are utilizing up to the 70% of their capability, then the string efficiency is 70. Here the formula for the string efficiency is the actual, in terms of current and in terms of voltage, both here there. So the actual in terms of current, the actual voltage rating of the whole string by the number of the number of SCRs in the string into the voltage rating of an individual SCR. Which means, suppose let me connect two thyristors in series. Okay, so then that is called as a string. So then the string, voltage, the actual voltage rating of the whole string, let me consider here 10 kilovolts. So here we are connecting the two SCRs, okay, and each SCR can capable of 5 kV. If the voltage or the voltage sharing across each SCR is 5 kV, then you will get 100% the string efficiency, because you can see here the actual voltage rating of the whole string is 10 kV and the number of SCRs in the string. So we have considered the two SCRs, 2 into, and the current, the voltage rating of individual SCR, which is 5. So 10 by 10, which is equal to into 100. So you will get 100% the string efficiency. Because here, as you can see, the voltage rating of an individual SCR is 5 kV, and here the utilization, the SCR is utilizing, because here the third factor, this factor is VOI is the voltage rating of the individual SCR. So here the voltage rating of the individual SCR is 5, okay, which means it is fully utilizing. So that's why here the string efficiency is 100. But in practically, this is not happen, because even though we need connect SCRs of the same rating in series, okay, so which means the specifications of the SCRs are same. Okay, let me consider in terms of voltage, but anyway for every SCR the ratings they mention in terms of voltage and current. Okay, but here just our understanding purpose, here we are just considering the voltage. So even though the specifications of the SCRs are same, but there are two problems mainly associated with them. Okay, so why we are getting, even though the same specifications of the SCRs, okay, but why the VI characteristics are different? Because of the unequal distribution of the voltage across the devices. That is the one problem, that is the unequal distribution of voltage across the devices. Okay, and the second one is the difference in the reverse recovery characteristics, which means during the turn on and turn off process, especially the reverse recovery characteristics during the turn off, because of the unequal distribution of the voltage across the devices. So the two thyristors may turn on or the turn off, may not turn on and the turn off at the same time. So if the two thyristors will not turn on and turn off at the same time, suppose here, let me consider here the two thyristors which are connected in series. Okay, and as we discussed before, so let me consider the voltage across the whole string is 10 kV, and here let me consider here the first, if it is equal distribution of voltages across the device. Let me consider, okay, if you overcome the first the problem, then with respect to the second problem, which means during if the turn on and turn off process is not at the same time of the thyristor T1 and T2, so which means here this is 5 kV and here it is again 5 kV. Suppose if both thyristors will not turn off at the same time, then suppose if the thyristor 1 is turn on before the thyristor 2, then the total 10 kV will appear across the thyristor T1, so that the thyristor T1 may get damaged, because the capability of the thyristor T1 is up to 5 kV only, but here we have applied the voltage across the string is 10 kV, but here only the thyristor T1 is turned off, but the thyristor T2 is not turned off at that particular moment. So it is turned off after some 5 or 10 microseconds. Okay, so but before that, here the total voltage across the string will appear across the thyristor T1. Then the thyristor T1 will get damaged. Right. So similarly, because of the unequal voltage distributions, okay, the turn-on process also at not at the same time. So how we can overcome these two problems associated with this series connection of the SCR? Because here you can see when coming to the forward blocking and the the reverse blocking characteristics. Okay, so here this black color representing the characteristics of the thyristor T2 or thyristor 2, and here the pink color, the dotted line, represents the forward conduction characteristics of the thyristor T1. Here, as you can see, the characteristics of the T1 and T2 are different, even though the forward blocking voltage are also different for these two cases. The forward blocking voltage is also different for these two cases. Then which means the voltage across the device is V1 and the voltage across the device is V2. So here V1 is not equal to V2. From these characteristics we can clearly observe, right? So that's why to overcome these unequal distribution of the SCR, okay, so we are what we have to do. So first we are concentrating on the first problem, that is the unequal distribution of the voltage across the devices. So further what we are doing is we are connecting a resistor in parallel with the thyristor, which means suppose if you connect n number of thyristors to meet the voltage requirement of a particular application. So we are connecting n number of thyristors which is having the same rating of an SCR or same specifications of an SCR. But as we know, the voltage distribution across each thyristor is different. So to overcome that, we are connecting a resistor in parallel with each thyristor. Okay, so then how to decide the resistance value of this thyristor? Because as you can see, the current flowing through each thyristor is different. Here is I1, here is I2. Okay, I mean like this here different, the current flowing through each thyristor, which means that the resistance may be different. So then how we can choose the resistor is, the resistances are such that the equivalent resistance of each SCR and the resistor pair will be same. The equivalent resistance of each SCR and the the SCR pair will be same, so that the equal voltage distribution or equal voltage division will happen across each thyristor. So in this case, the shunt resistor is called as a state equalizing circuit, which means if you connect this shunt resistor, then that circuit is called as the state equalizing circuit. But in practically, the different rating of the resistors is very difficult to connect across each thyristor, because here how I mean, according to this statement, okay, so the resistance that we are connecting across each resistor, or the value of the resistance, okay, so which must be is depends on the equivalent resistance, or the equivalent resistance of an each SCR, because the equivalent resistance of an each SCR is made different. So based on that, we have to choose the resistance which we are connecting across the each thyristor. But in practically, the different rating resistors, connecting different rating resistors across each thyristor is difficult. Then how we can choose the resistance, okay, which must be connected across each thyristor, the value of the resistance. So further here, what we are going to do is, so here we have divided the total string into two parts. One is the first part. Okay, let me consider there are total n number of thyristors are connected in series, and here this is the first thyristor. So, and the remaining part we are considering as a n-1 SCRs. Okay, this is the first SCR, and the remaining are we are considering as a n-1 SCRs. Then here the voltage across the string, okay, the voltage across the string. So let me consider here, here the voltage across the SCR1, the voltage across the SCR1, here we are just considering as the VBM. So which VBM is equal to the current flowing through this resistor is I1, and the resistance value is R, right? So that's why here I1 into R. Then the remaining part we are considering as a n-1 SCRs. Then the voltage across these n-1 SCRs, the voltage across these n-1 SCRs, which is equal to n-1 into, which means the number of SCRs into, here the current flowing through each resistor is I2 into, and again the resistance is R. Then the total resistance, which is Vs, let me consider the voltage across the voltage across the string, which is Vs. So Vs is equal to here the voltage across the, what is that, SCR1, which means voltage across SCR1 plus the voltage across n minus 1 SCRs, n minus 1 SCRs. And again here, let me consider the leakage current. The leakage current, of course, if the SCR is turn on, I mean turn off, there should be no current. But here, let me consider the leakage current in the SCR1 is, let me consider here is IBMN, and the leakage current in the remaining n minus 1 SCRs here we are considering as a IBMX. IBMX. Then the total voltage across the string Vs, the total voltage across the string Vs is equal to, so here the voltage across the SCR1 is I1 into R plus, and then the voltage across the n minus 1, what is that, SCRs, which is equal to n minus 1 into I2 into R, n minus 1 I2 into R. Then which is equal to, here the voltage across the, what is that, the thyristor 1, here we are just considering as a VBM. Then VBM plus here n minus 1 into, so here this one I am just writing as I2 as I minus IB max. I minus IB max. Okay, so how I have written this one is, because as we know I1 is equal to I minus IBMN, and similarly from this we can write I is equal to I1 plus IB minimum IBMN. Okay, and also from this n minus 1 SCRs we can write I2 is equal to I minus IB MX. I minus IB MX. So from this equation, so here before here I2 is there, so in the place of I2 we have substitute not MEX, MX here. So I minus IB MX. Then in the next case, so the Vs will become VBM plus n minus 1 into R, okay, and I1 plus IBMN, let me see, IBMN minus IBMX. So we can simplify this again as VBM plus n minus 1 into R into, so here I am taking just minus as a common, so I1 minus, if I take I1 as a common, then IBMX minus IBMN, right? So here just I am considering if delta IB is equal to IBMX minus IBMN, right? So just I am considering the IBMX minus IBMN as a delta IB, then you can just substitute in the place of IBMX minus IBMN as a delta IB, then this equation will become VBM plus n minus 1 into R into I1 minus delta IB, right? So then we can furthermore simplify this one as here VBM plus n minus 1 into, just I am what is that, multiplying this one, so n minus 1 R into I1 minus n minus 1 R into delta IB. So as we know from this equation here, that VBM is equal to I1 into R. So this thing here, just I'm substituting here in place of VBM. So I'm R in place of I'm furthermore simplifying this one. Okay, so which is VBM plus R into I1. So here R into I1 is what is that, VBM again. So the same VBM here I'm substituting. So N into VBM minus VBM minus N minus 1 into R into delta IB. So here plus VBM minus VBM get cancelled. Then here you will get N into VBM minus N minus 1 into R into delta IB. So if you further simplify this, then because actually why we are going to derive this equation is, so we are going to find the R value. Then R equal to N into VBM minus Vs, because here Vs is there, Vs by N minus 1 into delta IB. So this is how we can find the value of the resistance, because as we discussed here, so across each thyristor connecting the different resistors is very difficult. So that's why here we are derived some mathematical equation, so that we can choose a common value of the resistor, okay, across each thyristor. Because again here the value of this resistor is depends on what is that, the delta IB, which means again the IBN, the leakage current across the thyristor 1 and the leakage current across the N minus 1 thyristors, which means the leakage current across each thyristor. It will depends on the leakage, what is that, current across the each thyristor. But actually practically, in any SCR data sheet, okay, so only the maximum blocking current, the maximum blocking current will only they mention, which is IBMX, which is IBMX. So the delta IB, which is equal to, what is that, we can just simply consider as IBMX. Okay, then here that this equation will we can rewrite as R is equal to N into, so that we are just considering IBMN is equal to 0, because as we know the delta IB is equal to IBMX minus IBMN. So here if you consider IBN is equal to 0, then we will be having only IBMX. So here R is equal to N into VBM minus Vs by N minus 1 into IBMX. So this is the final equation. So based on this equation, we can what is that, decide the value of the resistance which we must connect across the each thyristor, so that we can make sure that the equal voltage distribution will happen across each thyristor, right? So this is how we can overcome the first problem, which is associated with this unequal unequal distribution of the voltage across each devices. Then what about the difference in reverse recovery characteristics, right? So here, as we can see, turn on and the turn off characteristics of the SCR. So these are the what is that, turn on characteristics, and these are the turn off characteristics of an SCR. As you can see here, the value of the the turn on, okay, because let me consider here T1 is the turn on, okay, for each in these two cases. Okay, let me consider, because based on that previous condition, so let us consider the voltage distribution across each thyristor is equal. Okay, the voltage sharing of each thyristor is equal, that is, let me consider it is Vs by 2. But still, even though the voltage across the each thyristor is same, but still the reverse recovery characteristics are made different. Because as you can see here, if SCR one assumed to have less turnoff TQ1 time than SCR2, which means then the SCR1 has recovered while SCR2 is developing the recovery voltage at T1. So both are developing the different reverse recovery voltages. So because of the both having the different reverse recovery voltages, as you can see here, let me consider here as TQ1 and TQ2. Okay, so here the TQ1 is the reverse recovery time of the thyristor T1, and the TQ2 is the reverse recovery time of the thyristor T2. So both are having the different reverse recovery time. Okay, both having the different reverse recovery times. So because of the different reverse recovery time, so the turn off what is that time is not, I mean, the turn off time is not same in both the cases. So if the turn off time is not same in the both the cases, because as you can see, even the turn on and turn off time. So when one SCR is triggered earlier, then the load will be shared by other SCR, and it may damage the other SCR. And in the second case, suppose if one SCR is turn off and other is still on state because of the different reverse recovery time. Okay, then again the total entire voltage across the string will apply across the one thyristor. Then the thyristor may get damaged. And how we can overcome this problem? This problem is overcome by connecting RC element across each thyristor. Okay, by connecting the RC element across each thyristor. Right here, this is the RC element that we are connecting across each thyristor. So this method is called the dynamic equalization. Before also we have connected, I mean, the resistor. Okay, so that is the state equalizing circuit. Okay, so by using this resistor, I mean, we are simply connecting this resistor across each thyristor. Okay, only just to what is that get the equal voltage sharing across each thyristor. So then from that process here we achieve that the equal voltage sharing across each thyristor, because here the total voltage is Vs, then across the voltage across thyristor 1 is Vs by 2, and the voltage across thyristor 2 is Vs by 2 again. Then by connecting an RC element across the thyristor, so we can eliminate, because here already the static equalization circuit is there here. Okay, so with addition to that, here we are connecting an RC element across the thyristor, each thyristor also. So that's why then if you want to eliminate the two problems associated with the series connection, then you must connect the static equalization circuit and as well as the dynamic equalization circuit. Because to get this, I mean, because as we discussed, okay, so even though the SCRs having the same rating, but they are having the different characteristics. So one characteristics are associated with the VI characteristics and another characteristics are associated with the switching characteristics. So that's why to make, because already we know the VI characteristics are also called as the static characteristics, and the switching characteristics are also called as the dynamic characteristics. So to make the static characteristics are equal, so here we are using the static equalization circuit, and to make the dynamic characteristics are equal, so here we are using the dynamic equalization circuit. So that what is that the over voltage across one thyristor can be eliminated, so that we can protect the different thyristors connected in series. This is about the series connection of the SCR. Then we are going for the parallel connection of the SCR, which means where the need the current rating is high demand, then in those cases we are just connecting the n number of what is that thyristors in parallel to achieve high current. Because as you can see, so let me consider the string current is I. Okay, then here I is equal to I1 plus I2. Again the same problem is also here, because even though the thyristor, I mean, just now we have discussed, even though the thyristor is having the same rating, but they are having the different characteristics because of the again unequal distribution of the current, because here I1 is not equal to I2. I1 is not equal to I2. So then how we can make this I1 is equal to I2? Because as you can see here, the conduction, the forward conduction characteristics of the two thyristors are different, because at a particular at this particular instant, okay, so the current flowing through the thyristor T2 is I2, and the current flowing through the thyristor T1 is I1. So which means here I1 is greater than I2 at a particular instant or at a particular voltage, but it should not happen. Okay, then how we can eliminate these things? Then here we are connecting a resistor in series with the each thyristor. There we have connected the resistor across or the parallel to the thyristor, but here to overcome, to make the equal distribution of the current through the each thyristor, so we are connecting a resistor in series with the each thyristor. So here, as you can see here, there are two different types of resistors for in every leg. Here RT1, RT2, RTN, and here R1, R2, and so on Rn. Here R1, R2, and so on Rn corresponding to the external resistance that we are going to connect, and the RT1, RT2, and so on RTN are the dynamic resistance of the various SCRs. The dynamic resistance of various SCRs. Then how we have to choose these R1, R2, and up to Rn values, because these RT1, RT2 are almost constant for particular resistance. So here this is the resistance R1, R2, Rn that we are going to connect in series with each thyristor. Then how we can choose these R1, R2, and so on Rn values in a way which equal to RT1 plus R1 equal to RT2 plus R2, and so on RTN plus Rn, so that the total resistance of an SCR is same. Then the current distribution, the current through each SCR will be also become the same. Okay, this is how we can eliminate the unequal current distribution by the each SCR. And one more problem is here is the unsymmetrical and symmetrical arrangement, right? Because here let me consider in unsymmetrical way and the symmetrical way. Okay, how it is unsymmetrical and how it is symmetrical? Because the unsymmetrical means here the distance between the thyristor T1 and T2 and the T1 and T3 is different. Okay, which means the distance between each thyristor is different. Okay, but in the symmetrical arrangement, as you can see, the distance from T1 to T2 and T1 to T3 is same, and T2 to T1, the distance between each thyristor is same. So because of the unsymmetrical arrangement, the unequal distribution of the current among the parallel connected SCRs due to the inductive effect offered by the conductors which carry current in the given configuration. Because even if you can see the T1, T2 and T2, T3. Okay, so here if you consider T1, okay, so the in asymmetrical, okay, so here the center thyristor T2 will have, okay, more inductance, as it will have the flux linkage from the T1 and T3 from both the thyristors. But if you consider T1 and T3, okay, so the T1 will have the effect from T2 only, but T3 also will have the effect from T2 only, but the T2 will have the effect from T1 and T3. So due to this reason, okay, the less value of the current will flow through the SCR which is present at the center than the outer two thyristors. So because of this asymmetrical arrangement also, so the current distribution among each thyristor may vary. Again, to overcome this, here we are arranged in a symmetrical way. So which means now here the effect of T2, T3 will be equal on T1, and the effect of T2, that from T1, T3 is also equal on T2, so that the current, flowing through each SCR will be also same, right? So this is how, by two, methods. One is by just connecting the each SCR, because as you can see, this is unsymmetrical way of connection, unsymmetrical connection, because here if you having one more SCR here, just only 3 SCRs, then here the inductive effect of on the SCR T2 from this T1 and T3 will be more, so that the current flowing through is less when compared to T1 and T3. That's why, not only just to connect the resistor in series with the SCR, so we must also take care about the configuration, how we are connecting the SCRs. That is also important to overcome the ununiform current distribution. Overcome the ununiform current distribution. This is about the parallel operation of the SCR. So the series operation of the SCR is required to get high voltage, and the parallel operation of the SCR is required to get high current, right? But while to get high voltage while connecting the two SCR, more than two SCRs in series, okay, there are two problems associated with that. One is unequal distribution of the voltages, or unequal the voltage sharing across each thyristor, and another one is due to the unequal reverse recovery time, which means one is with respect to the static condition, another one is with respect to the dynamic condition. So that's why there, to overcome the first problem, okay, then we introduced the static equivalent resistance circuit, and in the second case, to overcome the second one is the dynamic equalization circuit we used. So by this connection, we can eliminate the two problems associated with this series connection. One is the unequal distribution of voltage across devices, another one is difference in the reverse recovery characteristics. Similarly, in the parallel connection, okay, again in the parallel connection also the same problem is happening, that is unequal current or ununiform current distribution by each thyristor. So to overcome that, what we are doing is we are just simply connecting one external resistance in series with each SCR, and we are choosing the value of that external resistance in a way such that RT1 plus R1 equal to RT2 plus R2 and so on, RTN plus Rn. And even though if you are connecting a series resistance with each SCR, okay, but still there is a chance of unequal distribution of the current among each thyristor connected in parallel. So to eliminate that, here we are connecting a symmetrical arrangement instead of unsymmetrical. Here we are arranging a symmetrical arrangement. So this is about the parallel operation of the SCR, and the next topic we will discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.